Sahar Ben Rached, PhD candidate in quantum computing architecture in UPC in Catalonia, and I'm the co-founder of QTunisia, which is the first quantum computing community in Tunisia, and it was founded since September 2020. So in this presentation, which is a general introduction to quantum computing, I will start with what is a quantum computer as a technology and as a machine itself. What are the quantum phenomena in quantum computing? Third point is what does a quantum computer look like today? Even though we are still at the very early stages of development of the machine, but it would be still very interesting to know what are the hardware technologies that are currently being explored in order to build the quantum computer. So why quantum computers are different, and what is the main advantage of using quantum computers over conventional computers, why we need them, and I will go through the milestones of the quantum computing development, even though it's a very, very short list. Milestones are coming, I would say, every week. And it's really interesting to follow up with the development of the technology, but I'll just go through the main milestones. And of course, I will end with fields of applications, and hopefully that will inspire you to get started in quantum computing, and maybe you will see an advantage of this technology within your field. As for the questions, I will be answering the questions after each point. Okay, so I will stop at maybe 2 to 3 slides, every 2 to 3 slides, and I will ask whether there are any questions. So let's start with what is a quantum computer. So a quantum computer is a computational machine, okay? And the main difference of quantum computers with regards to conventional computers is that it is based on a new phenomena of nature, which are mainly two. First is called the superposition, and the second is called entanglement. And these are the key phenomena that make quantum computers powerful. So the main advantage of using quantum computers is to deliver more important processing power. And this means that quantum computers will have very specific applications, which we will refer to as complex algorithms or complex problems, in which we have the conventional computers we have the classical computers to be in shortage, or let's say in shortage of power of processing, and that means that they cannot solve the problem we want to solve within a reasonable time. Okay, and that's where we switch to quantum computers. So quantum computers are expected to outperform even the most powerful computational machines available today, which we refer to as supercomputers. Even though they are very, very important machines and we still need them, and we probably will still need them in the future, but still quantum computers will be used for solving even more complex problems than what supercomputers can do. So in analogy to conventional computers, quantum computers have an information unit that we refer to as quantum bits. Okay, so we have the bits in conventional computation, and we have the quantum bits in reference to quantum computers. Or in short, we can call them qubits. Qubits, physically speaking, are based on atomic or subatomic particles, such as photons, electrons, or the electron spin, which is an inherent property of the electron. And it's the way that we can engineer this type of particles to create an information unit that eventually gives us the quantum processors. So quantum computers are supposed to be their efficiency is supposed to be scaling with the number of qubits. So that means that the more qubits we have, the larger the quantum machine, and the higher the processing speed that we have. Now, today, let's say the most powerful quantum computer that we have is, let's say, in a few hundreds of qubits. Okay, so the latest release of more than 400 qubits from IBM Quantum, but that means that there are also other machines that have a similar number of qubits or even more. However, the main goal is to reach millions of qubits in one processor. Okay, and this is the goal of this decade. So in this picture, we have a processor that has 7 qubits. Okay, so this is a very small chip that dates to 2018, that was released by IBM Quantum in New York. And this chip has 7 qubits, but of course today we have a chip that supports hundreds of qubits. This processor is actually installed within an entire system in order to use this chip for computational purposes. So what are the quantum phenomena in quantum computing? So I already introduced two terms, which are superposition and entanglement. And these are two phenomena that you will hear a lot about when it comes to quantum computing. And the key to understanding how quantum computers work is understanding how superposition and entanglement can be used in order to create circuits and to do computational tasks. So let me start with superposition. So superposition is creating a quantum state that is a linear combination of 0 and 1. So it's common knowledge that the bit, which is the classical unit of information, can only have one value at a time. The bit can be either 0 or 1 at a time. However, the qubit can be in a linear combination of the states 0 and 1. Generally speaking, it is written as alpha 0 plus beta 1. Alpha and 0 have constraints to set the value of. They are complex numbers, but still we need constraints to say that this is actually indicating a quantum state or not. For example, we have the state 1 over square root of 2, 0 plus 1 over square root of 2, 1. This is referred to as the highly superposed state, okay, which is exactly a linear combination of 0 and 1 with the probability of having the states 0 and 1 50-50 each. I will explain about the probability in the next slide. Or a qubit can also have a negative value, okay? Value in quotes, because we call it specifically a state. The state can be negative, for example, -1. And this actually opens the computational space to an infinity of possibilities of states rather than just having 0 and 1 to do the computations with. Okay, so this is the main advantage of quantum computers. So please refrain from saying that the qubit is 0 and 1 at the same time, because this is mathematically wrong. Logically speaking, we say that the qubit is a superposition of 0 and 1 states, which means that it is a linear combination of 0 and 1, which is the mathematical definition of what a qubit is. So the main difference, or the first difference between a conventional computer and a quantum computer, comes to the unit of information. The qubit has an infinite possibility of states. Rather, the conventional computers can the unit of information can only be either 0 or 1 at the same time, at a time. So this is for the superposition. As for the entanglement, now the entanglement is a strange phenomenon, I would say. However, it's a very, very powerful one. So let's start with the definition of what entanglement is. So entanglement strongly connects two or more qubits so that their quantum states are no longer independent. Entanglement is maintained across vast distances and spaces. So the idea is that we can get two qubits, at least two qubits, to interact together and to create what we call an entangled state. This entangled state has a very specific mathematical constraint. Of course, this is a technical definition, but you will learn more about it once you start digging into quantum computer. But the main idea is that two qubits are no longer separate, but rather together they create one system, or they create one state together. Okay? The idea behind entanglement is that we can create large connections between qubits, which enables us to do computational tasks that rely on this dependency between the states. And if you learn more about quantum algorithms, you will learn more about how entanglement can be a very powerful task or routine in order to create quantum circuits that solve problems in a very efficient way. Okay, so the interesting part is that entanglement, even in nature, when we get two particles to interact and they eventually create an entangled state, is that this state is maintained across vast distances. This means that if we get two qubits to interact and then we separate them through long distances, thousands of kilometers, millions of kilometers, this entanglement stays the same. If we measure one qubit, the second one will get a state that we can predict based on the entanglement created. Okay, so superposition and entanglement, they do not have any classical counterparts in computations. Okay, so this means that these are very specific quantum phenomena, and we got to exploit them in order to create a computational machine out of them. It's very important to understand how we can use superposition and entanglement to create quantum circuits, even though it is still very challenging to understand what is the natural phenomena behind entanglement and superposition, which is an ongoing research. And of course, there is a lot of open questions regarding this. You can read a lot about it, but the main idea in quantum computing is how you can really use them in order to create a machine that is very powerful to solve complex problems. So, in addition to superposition and entanglement, measurement is actually very, very special in quantum computing, because quantum mechanics is a probabilistic theory, I would say, and this means that unless we measure the particle, we cannot be 100% sure of its state. Okay, and we cannot get any useful information unless we measure that particle. However, the measurement is also probabilistic. This means that we need to learn how to read the quantum measurement results. So measurement, as in definition or by definition, is the action that forces a qubit to be either 0 or 1 based on the probability of the state. I will get back just one slide. Here, the qubit in general is defined as alpha 0 plus beta 1. Alpha and 0, they tell us about the state. And in reality, they tell us about the probability of measuring the state 0 at the end of the task, or the probability of measuring the state 1 at the end of the measurement task. So alpha and beta, they show up in the measurement results. And this is an example of a histogram that shows the measurement at the end of a computational task that is done that is done based on a circuit of 2 qubits. Okay, so as you can see here, we have probabilities. We have probability of 30% almost to measure the state 0, 0. We have 18% to measure the state 0, 1. We have 31% to measure the state 1, 0. And we have 18% to measure the state 1, 1. So what are the states even 0, 0, 0, 1, 1, 0, 1, 1? If we have 2 qubits, okay, this means that we have 4 combinations of states. Okay, so either the 2 qubits are in 0, 0, or they are in 1, 1, or anything in between, which are 0, 1, and 1, 0. However, the quantum circuit would give you what is the probability of measuring each state at the end, based, of course, on the operations that you have applied on your qubits. And the idea is that how we can extract useful information from such a measurement result. It's not always straightforward. It's not always easy. It really depends on the algorithm that you are trying to execute. That means that we need to understand what the states would be referring to. Okay, and this actually makes quantum algorithms a bit challenging to understand, but once you get the main idea, once you know how you can exploit entanglement and superposition to create circuits, of course, for a certain task, then by the end of the measurement, you can extract useful information from your results. So, how we can operate on qubits? Since we are still at the very early stages of the technology development, this means that we are still learning how to operate on qubits, and we are still operating on them using gates. So, if of course you went to an engineering school, then you must know that the logic gates, that such as AND, NOT, XOR, NOR, whatever, the logic gates that we use in order to operate on our bits, and our most basic layer of computation, our conventional computers. The equivalent of that also exists in quantum computing. That's how we actually can operate on our qubits, and we can start from a specific state and reach a certain outcome. However, quantum gates are different from the conventional or the logical gates, okay? And it's a totally different mathematical theory, and it's an entirely different operations that we need to use in order to do the computational tasks. Just to give you an example, we have gates such as the X gate, Y gate, Z gate, and the Hadamard gate. So these are quantum gates. Besides the X gate, which is the equivalent of the NOT gate in the logical system, the Y, Z, and Hadamard gates, for example, they do not have any counterparts in conventional or in classical computations. Okay, so these gates actually have very specific actions that we can operate on qubits to alter the state of the qubits and make it evolve to a certain outcome. And it's the sequence of operations or the sequence of gates that we apply that makes our circuit, and eventually that solves a certain problem or executes a certain algorithm. The Hadamard gate, for example, is the gate that we use to go to the superposition state of qubits. So for example, if we start with the state 0, which is the initialization of our qubit, and we directly apply the Hadamard gate, we will reach the state that we call state plus, which is mathematically speaking this one, which I have introduced before, which is 1 over square root of 2, 0 plus 1 over square root of 2, 1. And this is a maximally superposed state. Okay, so it's very easy to reach superposition actually. You can just apply a specific operation from, of course, a known initialized state, and that's how you can get your qubit to be in a superposition state, and that's how you can unlock the computational power of quantum computers. So, any questions at this stage?
Maybe one from me. Are there any other kind of gates?
There's a lot of gates. There's a lot of gates. These are only 4 examples. We've got the X gate, the Y gate, the Z gate, and the Hadamard, which are gates that we can apply on 1 qubit. However, we can even apply gates on 2 qubits or 3 qubits simultaneously. And of course, the list is very long, and each operation has its own action and its own value to its own action to evolve the quantum state. So you can just type in quantum gates and you will see that there is a lot, but we usually start with a basic set of gates, and the combination of these gates that would give us more complex operations. Okay, and among the most basic set of gates that we use in quantum computing is the XYZ gate, for example, for the single qubit gates.
Okay, so there is another question. Why the probability of 0, 1, and 1, 1 is almost the same, and the same for 0, 0, and 1, 0?
Okay, so this is an example of a measurement state, of a measurement result. So this means that I'm not even sure what this circuit is. Okay, there is so depending on what the circuit has evolved the state, you will get the measurement results. And since I don't know what the circuit is, this means that I cannot explain the measurement result that I have in front of me. But this is only to show you what a quantum measurement result looks like. I'm not here trying to explain a certain outcome. So what does a quantum computer look like today? The idea is that we are still at the very early stage of quantum computing, and this means that we still have a very long way to develop an entire system for quantum computers. This means also that we have a lot of research effort to come up with a technology, an entire system, okay, in order to build a quantum computer. So I showed you before a quantum chip, and I told you that the quantum chip is actually installed in an entire system in order to be executable or to be functioning, okay? So what I have presented before is what we call a superconducting quantum chip. This means that we are using superconductors in order to create qubits and in order to create the quantum processor in the end. And this means that there is an entire system, electronic system, in order to operate on these chips. So this is what IBM Quantum or IBM Q system looks like. This is the control system, which is the golden system here. It's also installed in a cryogenic system, okay, that gives us a temperature that is almost zero Kelvin, okay. So it operates at about 15 to 30 millikelvin, which is very, very, very low. It's even lower temperature than the coldest point ever discovered in the universe. And this is very important to reach the superconducting state and to start operating on qubits properly. Okay, so in order to create the environment for quantum processors to function properly, it's also a very challenging task, and there's a lot of engineering effort in that area. So one of the two of the most famous companies to work on superconducting qubits are Google and IBM. And this technology is also one of the most advanced technology as of today to create qubits. But it's not the only one. There's also a very good candidate to create qubits, which are ions. Okay, and trapped ions specifically are controlled using lasers. And they are also a very important technology, and we have already witnessed a very good outcome, even though it has a very big challenge in scalability. That means that it's very hard to create processors of hundreds, thousands of millions of qubits using ion traps, but we never know what the technology will get us in the future. So other technologies are the spin qubits or quantum dots. Okay, this is also based on semiconductor technology. We have also topological qubits, and there's Microsoft that is investing heavily in creating quantum computers using topological qubits. But this is a very, very early stage technology, I would say. Even the theory is still under development, let alone the engineering of it. But again, we never know what the research will get us to in the future. There's also diamond vacancy qubits, which are also very interesting, but still under development. So most of these technologies are still developed in research labs. Not many of them are available commercially. So besides ion-trapped qubits and superconducting qubits, maybe some of spin qubits, even though their machines are not really functioning properly. But we will see also where the development will get us. But yes, we are mainly at the research stage at this point. There's a lot of work to do to build quantum computers, and especially to scale quantum computers. This means that if the goal is to have a quantum processor of millions of qubits in order to see the real computational power of quantum computers, then I would say that there is still a very long way to go. However, there's a lot of effort, there is a lot of investment in this area around the world. And there's a lot, of course, of focus towards this goal within the next 10 years. So I would say, I'm very optimistic, I would say, that within the next few years, we will see many of these technologies available commercially, at least for initial testing. I'm not very keen on the idea that quantum computers will really make a huge difference within the next 10 to 15 years. But of course, if we can see the concentration of efforts within one focal point, then of course the efforts may give us a very, very good outcome. And probably we will see very good applications, commercial applications of these technologies in the near future. So maybe this is very interesting to people from coming from physics background. I understand that hardware technologies are not very easy to understand, I would say, but of course, there's a lot of resources to learn more about quantum hardware technologies. So no matter what the technology is, and there's a lot actually, it wasn't just for the 5 that I have mentioned, we have to choose these technologies based on what we call the DiVincenzo criteria, which are 5 criteria that would decide whether a technology is a good candidate to create quantum bits and eventually quantum computers or not. These 5 criteria are: First of all, we need to be able to define qubits using a technology. And then we need to be able to initialize to a pure state. Usually it's the initialization to the zero state. And then, in order to operate on these qubits, we need to define, technically speaking or physically speaking, a universal set of quantum gates. We need to know how we can control the state of the qubit in order to evolve and later on, of course, give us a certain outcome. And then we need to know how we can do qubit-specific measurement, be it single qubit measurement or any other type of measurement. There's a lot of types of measurement, of course, but the idea is that we need to have a full control over the evolution and the measurement of the states. Also, we need to have a long coherence time. So coherence time is one of the most, I would say it's the biggest challenge in quantum computing. What's the idea behind coherence time? So it's an inherent property of atomic and subatomic particles to not keep their excited state for a long time. This means that if we excite, for example, an electron, it will only be a very short time before it gets to its initial state, which is state zero. Okay? And we say that these systems, they like to be in a very lazy state. This means that once you excite them, they would prefer not to stay in very long excited. And this is actually very challenging. Why? Because if we excite our particles, this means that we have applied an operation. And if the particle does not keep that state for a long time, it will be very hard to control it and eventually do a right measurement. So we would need to create qubits that can be in an excited state for a long time that will enable us to do the measurement correctly. This is very hard because practically we are in a challenge with nature. Okay, this is an inherent property of these particles, but like they have advantages, which we will see in the next slide, they have also disadvantages, and the idea is that this is a common disadvantage in all of these systems. But of course, there is a lot of theoretical and engineering effort in order to come up with solutions with regards to this challenge. So, why quantum computers are different? I've been saying that they have a powerful processing or a high processing power, but how is this even possible? So, the idea is that quantum computers enable us to do computations simultaneously. Okay, so for example, let's start with the very basic machines that we have today, which we use, of course, in our everyday life without really thinking about how they operate and at a very, very basic level. So we have the bit, right? The bit can be either 0 or 1. And the byte, of course, which has 8 bits, can handle or can operate up to 256 different values, right? So the idea is that out of these 256 values, we can only have one value at a time. Okay, so it's an incremental process. One state, one value, and the next value, and then the next value. We cannot have two values at the same time in the same system. However, in qubits can encode all these 256 values at the same time. Okay, we just need a very, very limited number of qubits in order to encode the 256 values at the same time. What's the main phenomena behind it? Is that superposition, but also through entanglement. This way, we can tightly connect connect qubits so that they can encode this large number of states at the same time. And this gives us literally an exponential growth in the amount of working memory of the working processors of our systems. Okay? Superposition is very, very powerful criteria of quantum computers. Because if we have a very small number of qubits, and the idea is that we can encode a very large number of data, okay, in a very small system. Maybe, of course, we will not need just one qubit to encode 256 different numbers. But also, we are sure that we will not need 256 systems to encode this information. Okay, and the idea is that we can work them. We can work on them in parallel. So let me give you an example. Okay, this is an example that will give you the idea of parallel encoding within a very small system, which I hope will give you a very clear idea of why quantum computers are having or have a larger computational space than conventional computers. How we can simulate the caffeine molecule? So the caffeine molecule has 26 atoms, which is more or less large system, but we can have much more complex systems. Okay, but let's concentrate on the idea or the task of simulating the caffeine molecule. So in order to simulate a quantum system, in this case the caffeine molecule, we need to look at the energy configuration. We need to look at the structure of the molecule and the bonds. And there's a lot of information that we need to be aware of in order to come up with an efficient simulation of our system. And the amount of information that we need in order to simulate such a system is very, very large. So the caffeine molecule, despite not being a very large system, still needs a lot of energy and a lot of resources to simulate. And this is very challenging for conventional computers. So this is actually a task that has been thought of very well, and it was very detailed in the book by Robert Sutor, which is called Dancing with Qubits, which I really highly recommend as an introduction to quantum computing. And in this book, they claim that the number of bits in terms of zeros and ones that is needed to simulate the caffeine molecule is estimated at 10 to 48 bits. And this is comparable to 1 to 10% of the number of atoms on Earth. Okay? And we need to know that when we do computational tasks, this means that we are consuming energy. Okay? This is not coming out of nowhere. And consuming 10% of the Earth in order to simulate a system that is not so large is basically impossible, or it's not reasonable at all. However, if we look at the idea of using quantum computers to simulate such a system, we would only need 160 qubits or quantum bits that would hold the same amount of information. So the equivalent of 10 to 48 bits is just 160 qubits. And this is a very, I would say, reasonable task. Okay, but of course, I need 160 perfect qubits that would operate with no errors, that would operate in perfect environment in order to give me this computational power. But just to be clear, that this is a thought of example. So this doesn't imply that we will get all the data into those qubits, or whether we really need 160 qubits. Maybe more, maybe less. But this is, let's say, more of a thinking or a thought of a task that would compare the computational power of the task of simulating the caffeine molecule using classical information versus quantum information. So the idea is that we have large information. We can use classical computer to do the computational task, for example, this simulation, but it will not be solved within a reasonable amount of time or with reasonable resources. However, the same amount of information can be encoded in qubits. And of course, it would be more efficient to use a quantum processor in this case rather than a classical processor. In terms of efficiency, of course, I'm talking about resources, and I'm also talking about time. And time is a very, very important factor in so many tasks. So is there any question, please, at this stage?
So how can I create a program where 0 and 1 or true or false is a combination of the two, and how to be sure that the wanted result is the one we will find?
So don't think of quantum states 0 and 1 as true or false, okay? Because it's not the same logic in bits, okay? It's a completely different computational logic that is not based on semiconductor physics. But the idea is that you can initialize your qubit to the state 0, okay? And you can excite it to the state 1. This means that you only need one operation, which is the X gate. The X gate is the equivalent of the NOT gate in Boolean logic, okay? Which is, if you apply NOT to the state 0 or to the value 0, you get the value 1. So once we have the states 0 and 1, we can also create superposition states. If we start from the state 0, we can apply a specific operation, which is called the Hadamard. The Hadamard will give us a perfect superposition of the states 0 and 1. Also, you can apply the same operation with an initial state that is 1, and the outcome will be also a perfect superposition of the states 0 and 1. So maybe I can show Hadamard gate. Maybe I can get an image. Yes. For example, this is a very, very comprehensive image. Okay, so we can start with the state 0, or we can start with the state 1. We apply just one gate, which is called the Hadamard gate, and we will get a perfect superposition of the two states. Okay? When we do the measurement, we will see a histogram of 50%, 50%. Okay, this is, for example, a Qiskit program. Okay, this is Qiskit is the IBM quantum platform for using quantum computers. So they have created a quantum circuit that has one qubit. Qubits are initialized to the state 0 at the very beginning. So they have applied the Hadamard gate. The Hadamard gate here is stated as the Hadamard as the H symbol. Okay, so and then they measured this qubit. This is the measurement symbol. So if we go to the result, we can see that 50% of the probability has given us to give the state 0, and 50% of the probability has given us the state 1. Now, of course, this is not a perfect 50%, 50%, because there is an error in the system. But ideally, it would be 50% 0 and 50% 1. If we have a state that is at perfect superposition, this means that when we do the measurement, there is a 50% probability of measuring the state 0, and there is a 50% probability of measuring the state 1. So, analytically speaking, we know what to get, and experimentally speaking, this is what we get. So this is how we make sure that our program is functioning correctly or being executed correctly. So in ideal case, you would always know what is the outcome of your program even before measurement. However, if we are working with large or complex algorithms, this becomes very challenging, and this means that you need to rely on your system to be functioning properly in order to extract your measurement results and to analyze them to have some useful information out of them. Okay, so the idea is that it's all in your program. It's all in about following your state evolution, and in the end you will get the outcome after the measurement. And usually this is what an outcome looks like. It is not intuitive, I would say, but once you start working with this, it will become very, very normal. So why we need quantum computers, especially at this stage of history? So first of all, we are witnessing the end of the transistors era. Why? Because the transistors have become too small and too compact in one processor to the point that quantum phenomena have started to manifest at this scale. And quantum phenomena, of course, they have their own effect on the system. And this means that we'll be bringing in more errors and more noise that's ever needed for our computational tasks. So practically, we have reached the maximum of the transistors era. the transistors technology. Second is that we have hit the limitation of parallel computing. Supercomputers are very, very highly performing, but still we are now at a very stagnant stage where adding more and more cores does not improve the overall performance. And the third point is that we are now witnessing more and more algorithms, more and more complex algorithms. We are witnessing more or larger data. We are witnessing a lot of problems that are too parametric or too much of information involved, or too many constraints involved, to the point that classical computers take too much time to solve. And time, as I said, is a very important factor, especially, of course, in some industries or in some technologies or some research areas. Then we would need results in a very reasonable time. So this means that even the most powerful supercomputers will take several years to solve problems above certain data size and complexity. For example, the factorization of a number with n bits, n being very, very large. We can conclude that we will need quantum computers at the next stage of technology development. So, what is the quantum advantage? So in comparison with classical computers, quantum computers provide higher storage capacity if we can build quantum memory. Because quantum memory, even fundamentally speaking, is not easy to build. It's even contradicting some theories or some theorems that we have in quantum mechanics, but we are working on that. We need also higher processing speed, okay, coming from quantum computers. And also, quantum computers, they provide accurate solutions to problems with high complexity. What I mean by that is that quantum computers will not be the solution to all problems with high complexity. But there are certain classes that quantum computers can bring in a good advantage over classical computers. Okay? So, the ultimate quantum advantage is achieved when a quantum computer solves a problem that a classical computer cannot. And this is what we refer to as quantum advantage. So when you read about a company reaching a quantum advantage, or when you read about in the news about a lab reaching a quantum advantage, this means that they have solved a problem that a classical computer could not solve in a reasonable time, but a quantum computer could do that. Okay? And this is mainly what we are looking for. We are looking for a quantum advantage. We are looking for problems or algorithms or computational tasks in which quantum computers will have an advantage in solving these problems over classical computers. And again, advantage means in terms of resources and in terms of time. The good news is that we have reached already the quantum advantage, even though it's not for very useful applications, but still it's a very, very good step. And this brings me to talk about milestones. So how did the quantum computer idea even start? So it started in the very early 80s when Richard Feynman, who is a very famous physicist, has envisioned quantum computers because his idea is that nature is not classical, and if we want to simulate quantum systems, we will need a machine that works with the same logic and the same nature of these systems. And this is what the idea of quantum computers, this is how the idea of quantum computers has started, is that we will need quantum computers in order to understand how the most fundamental systems of nature work. Because quantum mechanics lays at the very basis of nature. And then this has, of course, attracted a lot of research. IBM has already started the investment in quantum computers since 1990. And then by 1994, the famous Shor's algorithm was introduced by Peter Shor, who is a mathematician who is still now working at MIT. He has developed an algorithm for quantum computers to efficiently factorize large integers exponentially quicker than standard algorithms. Now, Shor's algorithm will be one of the most important applications of quantum computers. However, we are still very far away from the real execution of this algorithm on a real machine. Because we will need perfect qubits, we will need a very large number of qubits to see a good result. But probably, of course, we will reach that in the near future. And then in 1996, Love Grover, who is also a mathematician, has invented, he's a computer scientist, sorry. He invented a quantum database search algorithm, okay, that has, of course, an advantage over all its counterparts in classical computation. This is also one of the most used or the most famous algorithms in quantum computing, and it's also very, I would say it's very intuitive to understand once you get the basics of quantum computing. And personally speaking, it's one of the best algorithms that shows you how really quantum computers work. In 2001, there was the first execution of Shor's algorithm at IBM's Almaden Research Center at Stanford University. This was the factorization of 15, okay, which is 3 by 5, but still, it was the proof of concept of a quantum machine executing a quantum algorithm. And since then, of course, research has accelerated towards the execution of quantum algorithms on real machines. By 2010, there was D-Wave. D-Wave was the first startup to ever work on quantum computing since 2000, I think. And D-Wave has announced their first commercial quantum computer, which is called D-Wave 1. Today, D-Wave has a machine that has more than 5,000 qubits, even though the physics of D-Wave machines is not based on superposition and entanglement exclusively, but rather it's based on other phenomena, quantum phenomena, that make it a very powerful computation machine also. In 2017, IBM has revealed a working 50-qubit quantum computer and the launch of IBM Quantum Experience. By the way, IBM Quantum Experience is free for you to use. You can just create an account on IBM Quantum Experience, install Qiskit, and start coding on your first quantum computer totally for free. Okay? So it's a very, very interesting task to do, I would say, if you want to discover about quantum computing. And it's also one of the most open platform in terms of community engagement, and also in terms of events, also in terms of educational resources. Today, IBM, of course, has revealed Osprey, which has more than 400 qubits and is still developing. 2 years later, maybe you have heard of this at some point, is that Google has announced its 54-qubit, which is a qubit machine, which is called Sycamore. And this processor was able to perform a calculation in 200 seconds that would have taken 10,000 years by a classical computer to solve the same problem. So this is a very famous paper in quantum computing. Of course, there's a lot of backlash. There's a lot of people who are saying that this is not real, but still, Google has presented its paper, it has presented its results, so it's for you to judge. The paper is available for free access. So if you'd like to take a look at this, it would be very, very interesting result. And then in 2021, there's a Chinese researcher group that has reported the world's fastest programmable quantum computer, which can run a calculation task 1 million times more complex than Google's Sycamore task. And it's also 1 million times faster than Sycamore. So within 2 years, we went from a task that could be solved in 200 seconds that would have taken 10,000 years by classical supercomputer to a machine that operates even 1 million times better. So of course, we don't have access to this machine, but this result was also reported in a free access paper for you to discover. And just to say that this is a very, very short list of milestones. The milestones of quantum computing technology and quantum technology's development is very long, and it's very updated every week, I would say, or every month. There is a big result that is announced, and it's really, really interesting to be living in this era when you can see the development of this technology. And if you would be following the news, then of course you must have heard about the Nobel Prize in 2022, which was given to pioneers of quantum information science, Alain Aspect, John Clauser, and Anton Zeilinger. Okay, who had very big contributions to the development of quantum information science itself, but also quantum computing. So since the announcement of this Nobel Prize, of course, there is a lot of attention that is even given more to quantum computing. And I would say that this will be even driving the interest and the investment towards the technology, but also hopefully it will be driving minds and brilliant people to the field, because there's a lot of shortage in the workforce in quantum computing, and anyone who would like to contribute in a way or another is very welcome. So just as a development roadmap, we are at 2023. So this year we are expecting IBM to give us the plus 1000 qubit processor. And this will be also a very big milestone, because we'll be overcoming the ceiling of developing quantum processors, because once we reach thousands to millions of qubits, then that's when we will be unlocking the real power of quantum computers. And this is, of course, expected to happen within this decade. So I would really recommend that you would be following the news regarding this technology, because there is a lot coming up. But also, this is a very detailed development roadmap that was announced in May 2022 by IBM. There's a lot of details about the applications, about the forecast for the technology development. There is, of course, the way or how it will be integrated as a commercial invention. And of course, this is a chart that will be resuming, or let's say focusing on the main points of the roadmap, but it will be very interesting also to see what this technology will be coming up in the very near future. But the main idea is that we will be reaching 1 million qubit within the next decade. It's not an easy task, actually. My PhD is focusing on how we can scale quantum computers to actually host millions of qubits, and I would say that there is a lot of challenges ahead, but it will be, of course, overcome, because at this point it's an engineering task. It's not a fundamental or scientific problem. The science is there. The science has proven that quantum computers work, and that quantum computation, quantum information science have an advantage in certain tasks. So now it's really an engineering task about overcoming the challenges that are coming from inherent properties of these machines, but also the scalability to 1 million qubit will bring its own challenges to the table. So it's an ongoing task, and we will see where the research will get us to. So as fields of application, there's a lot actually, but the main reasons why we are developing quantum computers is for cryptography. I would say cryptography is a very, very important application field. I would say it's really striking the rivalry between countries. It's actually cryptography. And we will see, of course, a lot of applications in this field coming up, especially that Shor's algorithm is already well developed. It has already been tested. Now it's about the implementation for security. And there's also medicine and materials, because I would say quantum computers, as they mimic the computing principle of nature, which is based on quantum mechanics, then this will help us to understand fundamentally how quantum systems work. And once, of course, we understand that, we can have a better idea about simulating new drugs, coming up with new medicine, and of course, developing new materials. There's also machine learning. Quantum machine learning is, I would say, one of the most hyped up applications, even though there is not really a clear idea about what quantum machine learning is, but there's a lot of research in that area, and there have also been a lot of claims about reaching the quantum advantage in quantum machine learning. But of course, it's still a very interesting idea to mix quantum computing and machine learning to come up with new ideas, maybe to encode information, but also about training and training speed up. And also maybe it will open possibilities to other results. And also searching big data, especially that we have already a set algorithm for this, which is Love Grover's algorithm for searching elements in big data. and it's already proven to present quantum advantage over its classical counterparts. And this algorithm is already being investigated and already being applied in many applications. So these are 4 domains of applications for quantum computing that are very, very promising. And we will see commercial applications, I would say, within the next 2 years. 2 to 5 years, I'm sure there will be a very big milestone regarding the commercial applications of quantum computing in this field. But let's wait and see. So thank you very much for your time and thank you for your attention. I hope this was a good introduction to quantum computing. I tried not to get into the technicality of it a lot, otherwise it would be very overwhelming. But still, I'm here to answer any questions regarding any part, and I hope this was useful to you. Thank you so much. These are my contacts if you ever want to stay connected, and I would be happy to answer your questions anytime.
Thank you very much for this presentation. It was really very fruitful. So we have maybe some questions. So first, as a newbie in the quantum computing, are there any advices to start in the world of quantum computing?
Yes, there's a lot of learning resources, I would say, but I personally started with learning resources from IBM. So IBM has Qiskit. Okay, so Qiskit is based on Python and it enables you to code on quantum computers, but also simulators. It's the documentation is very extensive. They have even a textbook for that. So once you type in, I don't know, Qiskit, and you will see they have even their own website. So you can, of course, install it. It's open source, so you can even contribute. There is also a lot of resources to learn how to use it. Okay, there's documentation. It's very, I would say, it's very extensive. And the interesting part is that they have a lot of application modules. So there is nature for simulating quantum systems. There's finance, optimization, and Qiskit machine learning. But also they have the Qiskit textbook. Qiskit textbook is very, very good resource. Okay, so this is an interactive textbook that gets you from the introduction about quantum computing up until the quantum protocols and quantum algorithms, but also research publications. Okay, there's a lot of contributions in this textbook, and they have even quantum labs if you want to test your knowledge. So it's really, really interesting. I would say Qiskit is the go-to educational resource. IBM hosts a summer school every year, so it should be in July. I would also recommend that you participate. There's also Qiskit YouTube. They have a lot of tutorials. If you want to, of course, I would say that if you're a developer, then you'd prefer tutorials on YouTube. Then I think that would be very, very good. But also, you would need your textbook in order to understand more of the code. Other than that, there are resources from Xanadu. Xanadu is a Canadian startup that has also a lot of resources in quantum machine learning. There's a lot of mentorship programs. There's the Qiskit community on Slack. If you have any questions or if you want to connect with a new group to learn together. And of course, there's a lot of books. I would say there is a lot of books like The Dancing with Qubits by Robert Sutor. It's a very, very good start. Yeah, there is also a lot of books. So there's no shortage of learning resources. If you want to learn quantum computing, then the last excuse you would give is I did not know where to start, because really there's a lot. But there's also QWorld and QTunisia. So QTunisia is affiliated to QWorld, which is an international associations in quantum computing, and they have very good learning resources. So I would suggest that you follow QWorld on LinkedIn, for example, and you can see when is their next workshop. Their workshops are happening everywhere around the world, and even as an international, you can sign up and you can participate. Also, QWorld resources are very, very good.
There is a question also. As a computer science student, should I have a strong foundation in quantum physics? If yes, may you suggest some materials to learn about quantum physics? And thank you for the presentation.
As a physicist, I would say yes. But pragmatically speaking, you don't need all of quantum mechanics to understand quantum computing, especially if you will be working on the software side, then you will need quantum computing for quantum information science, I would say. So the idea is to look for resources, not for quantum mechanics, but quantum information science. Because reading about quantum mechanics, of course, is very interesting, but also very overwhelming, and you don't want to spend a lot of time in that. But if you find good resource for quantum information science, then again, Qiskit textbook is very good. It starts with what you need from quantum mechanics for quantum computing, but also there's a lot of textbooks everywhere. I mean, there is one that I would recommend, but it's also oriented towards communication, quantum communication. So maybe it will be too overwhelming for you. Yeah, I mean, then you can just like type in quantum information science. Just don't type in quantum computing, quantum mechanics, because that would be too much. Quantum information science learning resources. Yeah, there's a lot. Okay. Yes, there is the QOSF. They have a lot of learning resources, I would say, from different platforms, because there isn't only Qiskit. There is a lot of libraries for quantum computing. But the idea is that you can always find something to read, but just look for quantum information science. That's what I would say.
I have a question, maybe a part of this. Is there any advice for the next generation regarding this area of field? So just maybe if you have an opportunity to go back in time so that you could tell yourself an advice. So what could it be?
So it's about being patient, I would say, because this is a research field and there's a lot of challenges to develop this technology. And I only started in this field because I really love what I do. I love working on really strange things and international secret projects, to be honest. So my personal motivation is always to say that, okay, maybe I will not live to see quantum computer functioning properly, but at least I'll be contributing to the best invention of the century. So it's just a personal motivation to do quantum computing. So it really depends on you, on what you want to do. There's a lot to contribute to, from the physics side, from the computer science side, software side, hardware side. There's a lot of shortage in workforce. So most probably, if you work in quantum computing within the next 5 years, you will graduate and have a job, whether you want it in research or you want it in industry. So personally speaking, I do not regret it, even as a professional choice, because I know that even the skills that I will learn and the things that I will discover along the way and the community that I will be part of is very, very enriching to me as a person, but also as a professional. So I personally love what I do, and I hope that this also inspires you to learn about quantum computing, because it really will be a hit technology within the next 10 years, 10 to 15 years. And depending, of course, on your patience, whether you want to start now or you want to start when the technology is a bit more mature, then of course that's a very understandable choice, because it's still very risky at this point. But yeah, it's a very exciting field, I would say, especially that I'm now starting as a young researcher in it. Then I really like the environment. So personally speaking, it's one of the best choices that I made for myself.
It's very inspirational. Here we have another question from our friend Richard. Is there any basic books you can recommend for quantum computing? There are lots of books, but most of them, even though take it basic, seems advanced.
Yeah, it's not gonna be easy. I'm telling you, it's not gonna be easy. So even if you go for the most basic book, you will still find it a bit challenging to understand. And why is that? It's because quantum mechanics and quantum computing are not intuitive. They are completely different from how we are used to coding and how we are used to deal with computers. So it's completely understandable. Just don't rush. Take your time to learn all the basics. Take the time to make it intuitive in your brains. It's gonna take some time, but eventually you will get there. The most basic books I would understand are Dancing with Qubits by Robert Tudor, and also the Qiskit textbook. And also there is another book. Let me. It's a long name, so I need to check it. Robert Loredo. Yes, book. Yes, it's called Learn Quantum Computing with Python and IBM Quantum Experience. It's very long, so I will copy it. And by the way, we have a community group on Facebook that is called Quantum Computing Community in Tunisia, and the pinned post is about learning resources. Okay. I need to update the list, to be honest, but I think it's a very good start. So if you want to join the group, maybe I can send the link. And once you get into the group, then you will find the learning resources at the very beginning.
Well, thank you. There another question. Would you plan to hold basic workshops that take quantum computing on a gradual step-by-step basis?
Yes, in QTunisia, we host workshops to start from the basics of quantum computing. We already hosted 3 or 4 introduction, so beginner level, and we hosted 1 advanced level. But QTunisia is currently on hold, to be honest. So we will see how the activity will develop in the next year. Hopefully, we will go back to being as active as before. But for now, it would be best to look at keyword pages. So that would be on LinkedIn or their website. You will find the workshops around the world, and you can sign up at any point you want. There's always a workshop somewhere in the world, so you can just like follow the news, and you can sign up to whatever community it is.
Thank you. So there's another question. Can the quantum computer be a threat for information security?
Yes, it is a threat to information security, and that's why there is even a race to build quantum computers, and that's why I said cryptography is the main reason why we are building quantum computers and striking a very big rivalry between the big countries, and that's why there is a lot of work regarding post-quantum cryptography. That means creating algorithms and systems that will be immune even to quantum computers. It's a very active area of research, and the main reason is that we don't want to reach a point where there is a quantum computer that is fully functioning, and at that point, the information security system around the world will be at a very, very high risk. Now, of course, there is a lot of time to develop a quantum computer that would function properly, but you never know what's really happening behind the closed doors of research labs around the world. So it is best to be ready at this point, and that's why there's a lot of research regarding this area.
Cool. There's another comment. Great to know you have a community page on Facebook. Do you plan to host a similar one on Discord or Slack?
Yeah, we have a Discord, but it's not active. I think the most active one is the Facebook group, and I haven't updated in a long time. So it's on me, I know, but we hopefully will be more active this year, and we will yes, we also have a Slack, but it's for the internal team. It's not open to everyone. But yeah, probably you can follow us on LinkedIn and on Facebook. It's QTunisia on both platforms, and if there is any new platforms that will be extending the community to, then most probably will be posting on social media. So that will be Facebook and LinkedIn. And I hope that this was very useful. If you have any questions, then please reach out to me on LinkedIn or by email, and I will do my best to answer it.